Hello. Are we on? Yes. Good evening. Good evening. It's gone dark outside. Thank you very much for staying around to the end of what is a long first day, and it's a long conference. A lot of stuff to get inside everybody. So, absolutely delightful. Thank you so much for joining me in the last session of the day. My name is Nash. I'm a developer relations engineer at a company called DataStax. Now, DataStax is building kind of an AI platform for building generative AI applications. We've got two kind of components to that. One is AstraDB. That's a vector database and NoSQL store, document kind of oriented database. And the other side of it is Langflow, which is an open source drag and drop builder for generative AI applications. If you're at all interested in kind of either of those, do come find me around the rest of the conference. I'm normally found in sort of purple stuff, although I realize I also match the chairs here, which is not great if I'm sitting down, I guess. Otherwise, you can also find me online all over the place as Phil Nash, or on Blue Sky as philna.sh, because that's genuinely my favorite domain name in the world. And then it turns out you can use that as your name now, even better. Cool. I think we started this conference with a kind of a wonderful session from Scott Hanselman on generative AI and kind of things and ways we could use it, and it really kind of I felt like a lot of that helped set me up to talk about what we're going to talk about today, which is also for the next hour, which is retrieval augmented generation and building RAG from scratch. I very much appreciated the kind of examples that Scott provided, in which it was very important what you told a model before and how that drove its output. And hopefully we're going to dig a bit more into that today. So we're going to talk about building stuff from scratch, hopefully so that we understand things. But actually, so it turns out that like the fact that you can drive the direction of what a model is going to say to you is sort of one of its problems, right? The fact that it really just wants to output and generate text. Or I'm going to mostly talk about text models and this kind of stuff. Like I recognize in generative AI we have image and video and all that kind of stuff. I'm mainly going to talk about text today. But the point is we can drive the output of models, but also these models are not full of data. The actual problem with them is that every one of our large language models has a training cutoff date, at which point it no longer gets new information kind of embedded into its being, and at any point, even if you were constantly training large language models on public data, there would still be private data that it couldn't possibly know about as well. And so, large language models cannot be up to date. They cannot know your private data, and we probably don't, in general, want them to know our private data. That's not bad. That's not a good thing. And really, the fact that we can use them, we can influence the way they can generate stuff. We can influence a model to tell us that the capital of the capital of France is Marseille, perhaps, with enough work. The fact that we can influence them like that does mean that sort of their knowledge is really just it's that emergent characteristic of it that we can't necessarily trust. We cannot trust a large language model, and therefore we must influence it. And so I have a demo that I've set up that we're going to play with for the rest of the evening, in which I'm building a chatbot to talk about stuff going on in the event. And this is very obviously, if we ask it about NDC London, if we ask what is Phil Nash speaking about at NDC London, it probably shouldn't know. So this is actually, so this application currently, right, I need more information to answer that. I don't have access to the schedule or speaker details. This is because this is actually talking to Gemini 1.5 Flash, so one of Google's models, just via its API. And that doesn't currently that's not set up to do anything else. Like if you actually talk to, I guess, like kind of the Gemini consumer app, it can go and search the web, go use Google to go look stuff up for you. But this is kind of a blocked off, simple model that just doesn't know stuff. And that's fine, right? This is up-to-date data and it doesn't know. So we want to get it to know. We're going to do that by the end of this talk. And we're going to do so using retrieval augmented generation, RAG. Retrieval augmented generation is, weirdly enough, is a technique that was invented in I think it was 2020, the paper came out, which was a couple of years before ChatGPT kind of revolutionized this whole thing. But people have been, for a long time, we've been building language models since the transformer architecture hit academic conferences in 2016. People have been building kind of language models, and they've been getting larger and eventually better. But the idea that kind of being able to generate content was at all useful led to, it was actually, I believe people at Meta, developers at Meta who kind of wrote the original paper on retrieval augmented generation and providing that to sort of BERT-style models that have been around for a little while now. But with the excitement of ChatGPT and then all the remaining, all the rest of the models that have fallen into our laps since, retrieval augmented generation becomes important. And the idea behind retrieval augmented generation is we're going to store our data, our up-to-date or our private data, some way that we can later look it up. We're going to have a user make a query against a bot, like what's Phil Nash speaking about at NDC London. We're going to retrieve relevant data about that query. We're going to provide that data as context to the model alongside that original query, thus influencing the way that the model is going to answer. The model then generates a response based on our context, and then ultimately, I guess, profit, right? I sell the bot to NDC London, to NDC in general, and we all walk away happy. So it turns out, actually, obviously, we talked earlier a bit about like how prompting can influence the model, but really the difficulty at this point becomes actually retrieving relevant data about a natural language query. Because this is a query unlike, the fact that we use these bots as more chat makes it our language, the way that we search or we talk to them, different to actually search. We're not trying to do keyword search. We're not trying to interact with a chatbot the same way that we would have done so with a search interface. So that's kind of interesting. So retrieving this relevant data is our difficult part here. And so when you break down RAG, it becomes that retrieval is the search side of things. Augmentation is merely adding it to the prompt. And there is some stuff you can do there, but it's really, that's not the most important part. And then generation is left in the hands of the model. And the actual retrieval part is I think the interesting bit to actually dig into. Dealing with search and natural language search is an interesting problem. And it's been around for, again, also longer than large language models have been around. But there's sort of a renewed interest in how it works and how search and natural language search is going to work for us. And so we're certainly not doing keyword search, as I said. Like, this is not the way we interact with a bot, with a language model. The search we want to do is by similarity, by not relevance as such, but similarity. We want to get the context out of our data that the user is asking about. And so that brings up the question, how do we capture meaning in text, in data, in a way that we can search for similar types of meaning? And the answer to that, at the moment at least, is by using vector embeddings. Vector embeddings are really interesting. They are effectively a list of numbers that represent the meaning of a body of text. Or they can be multimodal. Again, we can represent images and other media as a vector embedding as well. There's a list of numbers, a point in a multi-dimensional space that represents the meaning of a body of text. And there are different ways to create them. But I wanted to start, this early part of this talk by creating our own kind of version of a vector embedding that, honestly, the first time I saw this kind of thing really helped it to click into my head what was going on. And so our hypothesis for this is if I want a bot, a chat bot, in which I can ask stuff about this conference, the titles and the descriptions of the talks going on at the conference kind of contain the meaning of those talks, at least abbreviated meaning at least. those are made up of words. And the titles and descriptions that share words are therefore similar. That's a reasonable hypothesis, I think. And so if we collect all of the words and represent each talk as kind of a count of each of the available words in the entire vocabulary of the conference, then that is a way, well, we can then take a user query, do a similar count of the words, and compare them somehow. We'll get to comparison later, but let's go and build this. So in the background of my application, I currently I have a connection to a bot. That bot is Google Gemini, as I said, and it's getting this kind of query and context. But right now, the context is found via this find similar talk function, which comes from this file, which ultimately returns nothing to it right now. So we're currently giving it no context whatsoever. But I have a few things set up for it. This is an entirely new file. I have some things, including a bunch of kind of common words, because common words are not really going to help us differentiate between talks. And then punctuation, which I would like to cut out. And then a few other bits, so we escape out, get rid of all the punctuation, and lowercase all the words, just to make things a little easier on ourselves. And once we've done that, we can take all the data. So I have, I scraped the website a couple of days ago for NDC London, and these are all the talk titles and descriptions. So you can see we have things like .NET, Aspire, and AWS. And I think my talk is down here somewhere. Build Rag from scratch. There we go, that's me. And so we got all the talks in there, and it's about, in this case, 100, apparently, although some of them are 2 parts of various workshops. So let's grab them. I've already parsed them out of that JSON file, and we're going to get all the words. Let's get all of the words. And we'll do that by taking talks and flat mapping against this text-to-words function. And that's going to give us an array of all the words in order of all the talks, which is great, but actually really I only want them in that array once. So we'll just make that unique. I am doing this in JavaScript. It doesn't matter that it's JavaScript. This is just my language of choice. You could be doing this in anything you wanted to. But with that all words array now, we should find that I'm just logging out the length of the thing, which is down right at the bottom of the screen there, to say we have 2,938 words are used to describe all of the talks NDC London this year. Nice to know. And if we just take a quick look at it, my console will give us the first 100 words to look at. But and those first 100 words are going to be that first talk. So we've got .NET, Aspire, AWS, Match, Made in Heaven from David Parman. Cool. That's not the most exciting thing. Let's take a word now. We take a set of text and turn it into our vector. So I'm just going to kind of I'm going to create a map of words. Oops, word map is I'm just going to use an object for that. And what do you, Copilot really likes helping with this, which is really nice of it. I guess it's seen some of this before, but really, we're going to take a word map. We're going to go. We're going to text to words the text that we pass in. And that text to words is the same that we used function we used here, which is all that's doing is cutting out all those common words, cutting out the punctuation, lowercasing it. And so we're going to take text to words for that. For each of those words in the word map, we'll count how many there are, and then we're going to go against the all words. Oops, we're going to return all the words mapped either yes. So we've taken that all word array, and then we're just putting in a map of the count of that word or 0. And so what that means is if I then console.log text to vector with, let's say, the first talk, I get this 2,938 size array where all the words happen to be in the first, 30 or 40 words there. And we can see right at the front there, this was the .NET, Aspire, AWS, so like .NET, or the word net in this case, is used 3 times in that talk, 6 times for AWS, 6 times for Aspire, I think it was. And all of that is at the one end. So actually, if we look at the second one, for example, the second talk comes out with, it shares a couple of words, right? We have a couple in there that are shared, and then mostly in the next bit. And so this is our vector. It's a sparse vector. Not a lot of overlap in the contents of them, but where they overlap is where it matters. And that, I think, is what's going to be interesting about this. As I say, we are sort of making this up, and it's not a very good vector to capture the meaning, but we should see it work. And so now we have this text-to-vector function. We can actually make an array of all of the talk vectors. So we'll take all the talks and map them into text-to-vector, although we'll return the talk as well as the vector. And so if we do that, oops, we'll get talk vectors. We look at the first one, and now we get the content, .NET Aspire and AWS, and its vector. And then so we have this array of content and vector of all of our talks. And so that sets us up nicely. We have all our vectors ready to compare against a user query when that comes in. It doesn't help the bot answer any questions yet, but it does present our initial data as something we can now use. See, comparing vectors is now the second part of this. Comparing vectors is the interesting part. See, what we've done is we've placed all of these words into this multidimensional space. In the case of our type of vector, we have 2,938 dimensions of space. It's really hard to think in 2,938 dimensions, so here are 2. And the idea is, in this case, I've plotted 3 points in a 2-dimensional space, and what we need to do is compare and find the most similar ones. But I keep saying points in a space, and that's not entirely correct. Vectors are not actually just points. Vectors are direction and magnitude from the center, from the point 0, 0 in this case. And because they're that, their sort of physical closeness is not necessarily the point. If you were to look at these 3 vectors and say which are the closest, you might pick the 2 that appear physically closest to each other. But because they're vectors, they're actually pointing in different directions, and the ones that are most similar are the ones that are pointing in the same direction. Their meaning is the direction, and the magnitude is just sort of how much they mean that. And so in this case, our vectors on the bottom, nearer to the bottom and further out to the right there, are the ones that kind of mean the same thing. It's just the one at the top there really, really means it. And that's still kind of abstract to think about, but that's how we're going to deal with this. What we're really looking for when we have all these vectors to compare is the smallest angle between them. And the way that you get to measure that is trigonometry, thankfully. We remember trigonometry from school, I hope. It's one of those things where I think teachers used to say, oh, you won't walk around with a calculator in your pocket, and then we do. Which is great, but they didn't mention that we might have to do trigonometry at some point later in our lives. I don't know. I avoided games development to avoid any of that kind of stuff as well, but it turns out that cosine similarity is our answer for the angle, or comparing angles between vectors. A cosine similarity of 1 is this pointing in the same direction. They are the same. A cosine similarity of 0 is that they really have nothing to do with each other, and -1 is sort of the opposing meaning. And we work that out by, I've always wanted to put a maths thing on a slide. You don't have to know what this is. But cosine similarity is this function, beautiful. And really all that is if we take the top part, is the dot product of 2 vectors. So that is, if you take 2 vectors, you multiply each member of the vector against its kind of opposing member, and then we sum all of those up. So that's the sum of the dot product of things. And then the bottom is the magnitude. So it's the square root of the sum of the squares of each vector. So you go through each item in the list of numbers, square it, add it up, and then square root the lot of it. And so we do that to each vector A and B, multiply that together, divide the dot product by that magnitude, and we get our cosine similarity, which lands between 1 and -1. Let's do that in code, though, because it's actually much easier in code than it is maths. Promise you. Let's dig in. So I had my talk vectors. Now we need the dot product. This is another one where Copilot does really try to help out, and I appreciate it when it does. But it's going to try and do it with complicated JavaScript, and I'm actually going to do simpler ones. So if we start with a sum of 0, it's so quick. We're going to go through the vector, and for each item in the vector, in vector A, we'll add the vector A item versus vector B item, and return that sum. Lovely. We then take the magnitudes. The magnitude is just of a single vector, and again, that's that strength. It's how far into the, how far away from the origin it's kind of pointing as a single number. And in this case, we're going to sum up the squares of each of the items in the vector. So it's actually very similar to dot product, except, there we go. Instead of using two vectors, we're going to just square the items as we run through them and return the sum. No, we return math.squareroot of the sum. And so that kind of brings it back into, because we squared everything, we then square root it, and that's our magnitude. And our cosine similarity is then just combining the two, right? So thank you, Copilot again. We return the dot product of vector A and vector B, and divide that by the magnitude of vector A times the magnitude of vector B. And if we go and take a look at that now, we can actually, we have our talk vectors, and we have our ability to calculate cosine similarity. So I can console.log the cosine similarity of, let's say we had talk vectors. Talk vectors. Okay, so talk vectors is this array of basically tuples of a talk and a vector. And so the vector is 0.1, is that part. So this is the first and the second talk together, and how similar they are. And according to this particular measurement, they are 0.03, 0.036. Not very similar, but if we remind ourselves what those were, actually, let's have a quick look. Console.log talk vectors. Yeah, so the first one is, .NET, Aspire, and AWS. And then the second one is about everyday real-world uses for Copilot. So not particularly similar talk titles. If you were to compare against itself, we actually find, oops, let me get rid of that for now. If you compare a talk against itself, you get 1, because they are the same. That's actually kind of nice. I've done this before, where the answer came out as 1.000003, because floating points, but so more similar than it could possibly be. And then if we picked a couple of ones that might be similar-ish, right? I got there's my talk, which is number 10. And if we compare, actually I compare that against the second one. I haven't done this one yet. This is comparing the one against Copilot. So 0.04 similarity, so my talk is slightly more similar in description to the one about using Copilot, which is about AI, than the one about .NET Aspire, which makes sense. And then I think if I take number 25, that's actually this morning's keynote, 0.02. That's because it mostly talks about like language models and very large and very small language models, and doesn't mention generative AI as such. It mentions language models, so it's less similar. But now we've done that, we can actually use this to find similar talks. And actually, well, yes, we can find similar talks because we've got our measurement and we have all our vectors created. So we can now get a vector for our query. So we're getting a new query in now, a new query made of new words that we maybe haven't seen before. And we can turn that into a vector. And then we'll return, yeah, that's probably the answer, isn't it? We're going to return the talk vectors, and we're going to map over them, and we'll take, I always like to do this, but I like to get everything returned to me. So we're going to map over them. We take all the existing talks and vectors, and we'll return both the talk, the vector, and then the cosine similarity of the new query vector with all of those vectors. And then we'll need to sort that'll do that. And we'll slice as well. Yeah, sure. So we're going to map over them. We're going to return the cosine similarity of the new query vector against all our existing talk vectors. We'll sort them by the highest similarity and then slice by a limit, which by default is 5 here. And when we do that, I can go back to my chat here. Well, actually, I have a search interface as well, which is not doing a chat. It's just literally asking for for our search for that this function we made, this find similar talk. And so if I ask about generative AI and RAG, then we get answers like, can Gen AI make the world disability inclusive? I do hope so, by Dunny de Klerk. A similarity score of 0.43 there. AI versus humans, a similarity score of 0.3. Funny enough, my one doesn't come up. I'm sure I did something for that. If I just search for retrieval augmented generation, because no one else is actually talking directly about that, then my talk comes up as a similarity of 0.24. And so we've created this vector. And so in this case, if I now go and ask the chatbot, so this is actually doing the rest of we've done the search there, the rest of the augmentation and generation. If I say, who is talking about retrieval augmented generation, question mark. But it answers, it knows, hooray. Phil Nash is talking about retrieval augmented generation, RAG. And if I was to ask, let's clear that chat just so it doesn't have any memory of it, like what is Phil Nash speaking about, which is the question I started with, it's going to say Phil Nash's session is titled Build RAG from Scratch. So we've built a really bad vector there. It's a sparse vector made up of just adding up numbers of words based on all of the words that we've seen. But it sort of has this capability still, even with low kind of similarity scores, to augment our generation enough to make it actually useful. It sort of works. And I think for me, it's this idea of like taking or making up our own vector in the most simple way possible by just adding word scores together. Adding word counts into a vector and doing that comparison using cosine similarity, that it's kind of, that made it click for me. It's straightforward enough to say talks that share the same words are sort of similar to the query or to other talks. But it is a very sort of, right? Like no one is using this in the real world. I really hope not anyway. Firstly, because we need to know all that data up front. Like I had to know all of those talks in order to create my vocabulary and be able to generate the vectors for all of them. It's sensitive to the vocabulary. So like when I asked about generative AI, a talk with Gen AI in the description is only going to match on the word AI and not gen and generative, and that actually happens in this particular set of data. It's also the case that if you use words that have not been seen in the set of words already, then you can never kind of compare against those. So that's not very useful either. We can only really get that similarity based on the 2,938 words that we looked at. But if you were to kind of continue to increase this and use all talks that have ever been given at any conference ever, you're probably just going to have more words, a bigger vector, more calculations, the whole thing's going to slow down. Which is not great either. And of course, the same word can mean different things. If we talk about something that's generative, or sorry, if I'm talking about something that's generative, I'm probably talking about AI, but it could be something biological where things are generating, being created. It could be something else. And even just the order of words, the idea that a classic example, I think, of this is the difference between man bites dog and dog bites man. Is fairly significant. Men should not be biting dogs. Nobody should be biting anybody. But the shock value of one is slightly more than the other, at least. And so none of that is kind of captured in this word counting, this bag of words kind of model that I've used. And so that brings us to the way that we really do it in real life, which is embedding models. So as part of sort of the training of large language models, the way that we break down incoming text to it in the training data is to turn them into tokens. So in this case, we've kind of made a word a token in our creation of a simple vector. But there are more complicated ways of turning words into tokens, and then turning those tokens into meaning based on other machine learning models. Those models learn from all that data to create this dimensional space that has that meaning embedded within it. These models started off as simple like words to vectors. I think it was around 2016 when Google came out with word to vec, which was a simple embedding model that just did one word at a time. But that has been improved upon, and models have been built where larger amounts of text can be turned into a vector embedding. Now, the size of the amount of text that you want to turn into a vector is another interesting part of this, and I'll get back to that later. But embedding models are now kind of available to be used. They're either open source ones available on things like Hugging Face, or all of the many of the large-scale language model providers will also have embedding models as well that have been used as part of that training. Now, it doesn't matter what embedding model you use compared to the language model that you're going to use, because they actually never kind of touch each other, so it doesn't matter. You can mix and match using embeddings from OpenAI to talk to a model from Google or Anthropic or whoever. But most of them are, as straightforward as calling an API method like this, and OpenAI's kind of API is simple enough to say, hey, use the text embedding 3 small model, which is up here, with this input, get a encoding format of float. There aren't any others, but you have to say it. And you get the embedding back. And in this particular case, text embedding 3 small gives us 1,536 dimensions. And that's a fixed 1,536 dimensions in which the space and its meaning kind of exists. Text embedding 3 large has 3,072 dimensions, double the size. Weirdly enough, it doesn't necessarily matter that it matters. So text embedding 3 large is a larger model, and so is more nuanced about how it places meaning into a vector space. However, there is also the case that you can lose meaning with more dimensions as well. It's very confusing. I'm not going to go too deep into that, though, because a theory of dimensionality is beyond me today, I'm afraid. I didn't mention, but I flew in from Melbourne yesterday, so I'm asleep right now. So we can create embeddings this way. This is nice and easy. Otherwise, if you can use an open source model by dragging it in from Hugging Face and run it in with something like a transformers library, that will work. And once we have these embeddings, the other side of things is we don't really want to spend a lot of time calculating cosine similarity for everything every single time. It's going to be a bad time. Actually works nicely and quickly when you only have 100 cosine similarities to calculate in my example there. But if we brew that up to a few thousand, tens of thousands, hundreds of thousands, depending on how many documents you have, we absolutely don't want to put JavaScript or any language through the pain of doing cosine similarity over 100,000 documents every time. And so that's where vector databases come into play. Although I think this is kind of interesting. I've put vector databases on the slide, but effectively, every database that I can think of these days has what we consider a vector index, and that's more accurate here. Some databases were built vector first, but since this has been a hot topic, every other database has kind of added a vector index. And I think that's kind of interesting because creating a brand new database today has got to be harder than adding a specialized index to an already battle-hardened database. And so that's something to compare when dealing with vector databases or vector indexes. As I said, I work at DataStax. We have AstraDB. It's a cloud-based database that's based on Apache Cassandra underneath it with a vector index that we added and is actually available these days in open source Cassandra as well. I'm also not a fan of writing Cassandra query language, so I like AstraDB because it's a document store. It deals with things that way. And so if you, in this particular example, if you want to add a document and some vector embeddings into AstraDB, you can do so by just taking a collection and inserting both the content and using then the special $vector property and passing in that list of numbers. That will allow you to then do a similarity search on that vector column based on content. Other things I think vector databases can do is to handle some of that embedding for you, and actually AstraDB will do that as well. You can set up a collection with an embedding model, and then if you pass the content in as $vectorize, and the content you want to turn into a vector, then the database can handle it for you, and I kind of think that's nice. Because then when you come to search it, again, you don't have to do the make an embedding, find an embedding. You can actually just kind of vectorize the query on its way in as well. Nothing stopping you, of course, using your own vector embeddings, and AstraDB doesn't have every vector embedding provider available to it, but that's just a kind of nice, easy way, I think, to work with this. And so when you do that, we can actually get much better examples or much better results. And so I have a already prepared vector search. So this is the same function as we had before, find a similar talk, but in this case, it is now using the vector database in the background, AstraDB. And so this is that collection for our NDC London data. It's been set up with that OpenAI text embedding 3 small. Speaking of small things, so is that text. Text embedding 3 small, so it has 1,536 dimensions, and we can see the content is all here. It's actually easier to see in JSON mode. So there's Modern Observability and Event-Driven Architectures by Martin Thwaites and Ian Cooper. And that's going to be a great talk, actually. Things about OPFS. And in this case, again, because the database is actually handling the vectorization for stuff, I can search for generative AI and RAG right here in the interface. And that's doing a similarity search. And so when it finishes, we'll see that the top one is, yeah, right, build RAG from scratch. Oops, build RAG from scratch, that's me. And then the second one, according to this vector embedding, this kind of thing, is can AI make the world of disability inclusive? Yeah, cool. That actually came up earlier when I was doing it with our old and bad vector version. So yeah. And we can see those different similarities. Like mine is the most similar at 0.831, and then it drops to about 0.75. And as you get below 7, things start to get normally a little bit less interesting. So 0.68 there is, can you trust your large language model? That's a great talk, actually, by Jody. Go see that, too. But they start to become less about retrieval, less about search, just more about AI in general, and then it drops off further from there. And so now hold on, if I go back to my server and I replace my bag of words there with the vector search version, that will restart the server. And if I go to the similarity search, I can go generative AI and RAG, and that should return my talk. Yeah, that's what we just. That's the exact same search we just did in the interface. Now we can see it in just my version of the interface. But if I talk about artificial intelligence, we can see different things. So we got Steve Sanderson's keynote. I think that's tomorrow morning. I can never remember. 0.75. We've got AI for humans, AI in video games. And the nice thing about this is I search for artificial intelligence, but none of these actually have artificial intelligence because nobody needs to write all of that anymore. They're all just AI, but the words artificial intelligence are embedded into the same space as the shortening AI, and that's why all those things come up. And that then means that you can say who is speaking about AI, and we'll get a bunch of answers. I'm going to returning 5 from the database here, so it's come up with 5 things. Yeah, Steve Sanderson, keynote, Michelle Frost about, Scott Hanselman, yeah, that's this morning's one. Layla about that in games and AI co-pilots and aircraft. Horrifying. Probably a very interesting talk. I think that's tomorrow as well. And so, and we can ask, what is Phil Nash speaking about? and we should still get the same answer, but it should be a lot more confident about it this time because that is now a similarity of 0.83. We're not feeding those similarity scores to the large language model. We're just feeding the context and letting it decide based on the query and the context what it wants to answer with. So it doesn't have to know how sure it should be based on those similarity scores. It's doing the working out itself. Cool. So that's kind of retrieval augmented generation. I mentioned earlier that like the size of the text that you might want to turn into a vector embedding is important. See, it's not been important for these talks in this case because most of the talk descriptions are fairly short. So some of these vector embedding models actually have limitations. All of the vector embedding models have limitations on how many tokens they can turn into an embedding, and normally they either fail or drop off anything beyond their maximum. But I think like the OpenAI text embedding 3 small and large can have up to, I think, 8,000 tokens, which is about 5,000 or 6,000 words, which is a lot. But you don't necessarily want to go to the limits of these models either. You see, when we do, when we take text and store it for retrieval augmented generation purposes, we actually really need to turn that text into a bunch of ideas, concepts that the large language model can ultimately use to answer a question. If you take too much text, then that's trying to capture too many concepts. It's actually going to, it's spreading that piece of text amongst the kind of vector space, that meaning space that we had, which might make it ultimately less similar to a targeted question about a single part of it. And so it's actually important to consider the amount of text that you, not just the amount, but kind of how you break up the text. In terms of talk descriptions, they are fairly, around a single point, the point of what we're going to talk about in a conference. But if you take a document that is 10,000 words long, then you might want to break that up into the paragraphs that it has. Maybe each paragraph would be a concept, an idea, or a bit of context. And so that's kind of interesting as well. We have both the limits of vector embeddings, but also the limits of the embedding space to understand the chunks of text as well. I got far too into chunking up data for text and wrote an entire blog post about this and how there are many different ways of going about that, which I haven't actually linked on these slides, but I will share out with them. So I wanted to cover that just because I think it's interesting. Which I think is also a weird thing to say because taking a large amount of text and turning it into chunks of text sounds like the least interesting thing. But when we're doing it in order to feed context to a model, it is absolutely fascinating. The ways you can go about it are really interesting too. And so that's retrieval augmented generation. We're going to store our data in chunks normally if we don't already have small bits of focused data like I happen to have in these talks. We're going to store them alongside their vector embeddings. We're going to use good, dense vector embeddings that actually capture meaning better based on machine learning models. There are many of them available, and they do have varying qualities. There are leaderboards on some of them. There are leaderboards in which you can kind of compare embedding models for how good they are, although it still actually, at the end of the day, tends to matter like what the subject is. Things like OpenAI's text embedding 3 models are good general models, but there's one company called Voyage who actually train specific embedding models for things like law and medicine, I think. And so if you happen to be in those areas, then like a specifically trained embedding model is actually really useful for you. So we store our embedding models, we store our content and our vectors, and then when we get that user input, we can vectorize using the same model, sort, return the amount of context that we want to, hand that over to our model, and generate results. I also want to point out that I think it's really interesting. I've been using Google's Gemini 1.5 Flash in this talk for my example. 1.5 Flash is both fairly quick and very cheap to use, but it's quite good at what it does. and it's very good at that synthesizing of context into an answer. But it's not the newest thing. Google is experimenting with Flash version 2, which is not quite sort of fully released yet, but it's an experimental version. But obviously the world has been rocked in the last week or whatever by DeepSeek and new models and these thinking models, and they're cheaper and incredible. And I just, earlier I was just like, can I put DeepSeek into this application? What would it do? And so the answer was almost yes. I haven't signed up for the DeepSeek API, where you can access their full R1 model, which is 678 billion parameters or something and requires hefty pieces of machinery to run. But I do have a Llama, and I was able to download DeepSeek 7B, which is based on the Qwen 2.5 model from Alibaba. I think if you were watching Scott Hanselman's keynote this morning, he used the DeepSeek 8B model, which is actually based on Meta's Llama. But I was able to, actually replace that section with this. And now using DeepSeek R1. Not the full-size DeepSeek R1, but that one. And so in this case, we're doing the same thing. I'm still doing the search against the vector database and handing the context over to the model, but now our model's different. And so DeepSeek is particularly characterized by its thinking part, which actually will come out here as well. So I've passed it the context, and it's going to think about it. It's going to think about it. Did I break it? No. There we go. Right, so it's doing its thinking. You see its little think tag there. Okay, I'm going to try and understand what he's going to talk about. But it's got the context already. And so this is actually really good at doing it. Hey, it knows it's related to large language models. So it's doing a lot of thinking. It's still thinking. So there's a lot of thinking to be done in these models, because these are the reasoning models. They're not actually necessarily built for question and answer kind of sessions like this. But it still works very well. So it's ended thinking there, and now it's saying, hey, it's actually probably written out a longer explanation of my talk than I did, which is quite... Thanks, DeepSeek, making me... Anyway, point being, in this particular case, we don't necessarily need to use a reasoning model in order to do this kind of thing, but it's also important to consider that the model, unless you are a company building models like this and trying to sell models to other people or produce them as open source, the model is never going to be your competitive advantage. You should always be able to, in this particular case, like in the context, I swapped out 5 lines of code here for 10, but some of that's just line breaks. And I had a brand new model using the exact same data and doing a very good job of it. So our retrieval actually is kind of the most important part of this, and understanding vector embeddings and getting that bit right is more important than our choice of models, which will continue to evolve and improve over time and just improve that generation. Getting the retrieval part right leads to good augmentation, leads to better and better generation as the models improve. And so that's kind of how RAG and large language models can work together to overcome those difficulties of large language models, overcome the fact that they have their training cutoff data, their data is cut off at the end of their training date, they can't know private data, and providing context like this also helps to avoid hallucinations and produces good, useful applications for us. I do have some links for some deeper bits on this. The version of Retrieval, there is a QR code on the next slide, which also links through to all of these as well. But what I described just now about using a vector representation of a chunk of data and a vector representation of a query is one way to do this, but it can have difficulty when dealing with terms outside of its training data. However, Colbert is a method in which you actually you vectorize every single word in a piece of content with a sliding window of context over the content, and that is actually really good at understanding stuff beyond its training data, but it comes with the downside that there's a lot more to store because you're doing a vector per word, and that's a lot harder to search against. So there There's trade-offs and trade-ons for that. But it's a really interesting, I think, read as to how RAG can be improved with Colbert. That's kind of interesting. Then another way of making our retrieval better is to use kind of knowledge graphs. Graph RAG has been a very popular term recently, and the idea there is to extract links between pieces of context so that when you do your initial similarity search based on the vector embeddings, you can then use links to other bits of context to kind of fill in gaps that maybe maybe weren't initially relevant to the search, but are relevant to the answer. And so you can do that using content. There's a couple of different kind of graphs you can do. Content-centric is kind of the idea of like links and keywords between things. You could use kind of entity recognition kind of stuff as well. But the content-centric one works really well and is a lot simpler to deal with. And the idea of, pulling in extra context that's going to help it answer the question is good. And then just for other things you can do with vector embeddings and vector databases, is one of the first things I did with AstroDB, which was to just do build a feature for my own blog where using vector search allows you to do similar blog posts at the end of a story, so you can keep people reading. I think that's a really nice usage of vector search that doesn't involve an LLM, and it worked really nicely. I used to do it based on tag matching, and that was okay, but actual similarity was really cool. So as I said, my slides and links are at that QR code. Thank you again for coming. Again, so retrieval augmented generation, I think, is going to be around for a long time, as long as generative AI is. You might seem to think, one final thing to say about this. Large language models are actually increasing the size of their context windows. And so like OpenAI's models can take 128,000 tokens. Gemini Flash is 1.5 million. Gemini 2 Flash and Gemini Pro 2.0 both take 2 million tokens, I think. But retrieval augmented generation is really useful because when you feed that context, you don't have to take up all those tokens. Tokens cost money. And the more targeted the context you provide a model, the better the results you get out of them. And so RAG is not going anywhere. It's really good to understand it, I think, from the basis, but hopefully this has given you a great overview and a great understanding of how to go about with RAG. Again, my name is Phil Nash. I'm a developer relations engineer at DataStax, and thank you so much for coming. And I will, I'm around for the rest of the conference, so do come and find me. I don't want to, it's the end of the day now, so I'm sure we're a little tired. I want to get out of here, but come up and ask any questions anytime. Now, later, whenever. Woo! Thank you.